Welcome to this explainer, specially crafted for the engineering students right here on the Trong BK channel. So, I want you to start by just imagining the absolute sheer scale of the modern plastic injection molding industry. We are literally talking about producing thousands or even millions of absolutely flawless, identical parts, and doing it with a cycle time of just seconds. It's wild. But how exactly is a plastic injection mold designed to make this happen so reliably? Well, as you'll see, it takes an incredible amount of complex engineering.
To really anchor these theoretical concepts in reality, let's take a look at the heavy-duty environment where this whole process goes down. Here we have a state-of-the-art injection molding machine. Inside a beast just like this one, molten polymer is injected under massive pressure. It's rapidly cooled and then perfectly ejected. It's a high-stakes, high-precision environment for sure.
And that brings us to the core focus of today's explainer, plastic injection mold design, and specifically the engineering workflow behind it. What you'll soon realize is that a successful mold design isn't just about, drawing a shape. It's this careful, highly calculated integration of product geometry, material science, and thermodynamics.
So, here's our game plan for today. We'll start with the anatomy of an injection mold, then move into product analysis and parting lines followed by runner and gating systems. After that, we'll tackle managing shrinkage and ejection, look at mold materials and machinery, and finally, bringing it together in CAD. But before we zoom in on the intricate parts of the mold itself, let's quickly map out this core engineering workflow. You see, sequence is absolutely everything in mold design. For instance, there's no way you can design an effective gating system until you've successfully nailed down your parting line and mold concept. It's a cascading process. Every single step depends entirely on the accuracy of the step right before it. All right, let's kick things off with Section 1, the anatomy of an injection mold. This cross-section brilliantly illustrates a standard mold assembly. At a high level, the mold is divided into two main parts. You've got the fixed half, which bolts directly to the stationary platen of the machine, and then the moving half. Notice the heavy-duty mold plates, the guide pins and bushings that ensure totally perfect alignment, the ejector plate system down at the bottom, and of course, the central core and cavity. That's really where the magic happens, and the molten plastic takes its final solid form.
Moving right along to Section 2, product analysis and parting lines.
Now this brings us to a really fundamental concept. Before even thinking about establishing the parting line, engineers have to rigorously analyze the product geometry itself. We're talking checking wall thickness, draft angles, and ribs. Then comes the parting line. This is the exact line of separation where the cavity and core meet, and figuring this out is huge because it dictates almost everything else. How easily the part demolds, whether you have to deal with undercuts, the overall cosmetic appearance of the product, and even the quality of the parting surface itself. Honestly, finding that optimal parting line is undeniably one of the most demanding tasks in mold design. But thankfully, modern engineers don't have to just guess. Today's CAD systems pack some incredibly advanced help functions. By projecting what's called a silhouette curve onto the part, which basically represents the visible edge when viewed parallel to the mold opening movement, the software actually helps generate the most efficient parting surface mathematically possible.
It's pretty fascinating to see how an elegant CAD workflow involves literally slicing a virtual, solid mold block right along that defined silhouette curve. By splitting this digital block in two, the software automatically generates the perfectly contoured core and cavity mold inserts. It's like a giant ultra-precise puzzle.
Let's transition into Section 3, runner and gating systems. Once the mold is split, we have to figure out how to actually get the plastic inside, and this flow path is absolutely crucial to the quality of the final product. The plastic melt travels from the machine's injection nozzle straight into the sprue bushing. From there, it branches out into primary and secondary runners, and finally, it squeezes through these narrow, restricted cross-sections called gates right before hitting the cavity. Depending on the specific design, these could be edge gates, pin gates, or submarine gates. They're meticulously engineered to separate the molded part cleanly, hold back any cold skin that might have formed in the runners, and they even heat up the melt through sheer friction right before it injects into the mold. But when designing these channels, engineers face a major economic and technical dilemma: hot runner versus cold runner systems. It's a classic trade-off. Hot runners basically act as an extended nozzle, keeping the plastic molten right up to the cavity. That means zero material loss, but they come with exceptionally high initial tooling costs. On the flip side, cold runners are way cheaper to manufacture up front. However, they generate a lot of scrap waste from the frozen runner system that has to be either discarded or reground every single production cycle. Okay, let's look at Section 4, Managing Shrinkage and Ejection. So, let's assume your flow system worked perfectly and the cavity is completely full. We're done, right? Well, not quite. As the plastic begins to cool down, a new physical problem pops up. Shrinkage in a plastic part is almost never uniform. Because you have varying cooling conditions across different layers of the plastic, combined with restricted thermal contraction, we get something called anisotropy. In plain English, that means the shrinkage differs depending on the direction of the flow. Radial shrinkage and tangential shrinkage simply aren't the same. Because of these funky dimensional changes, the design engineer has to heavily modify the initial CAD geometry, effectively scaling it up with extreme precision, just to guarantee that the final, cooled part meets those strict manufacturing tolerances.
That brings us to Section 5, Mold Materials and Machinery.
You know, a perfectly calculated, scaled-up cavity is completely useless if it's machined from the wrong type of steel. Material selection is always a game of compromise. For instance, if you want to make machining easier and avoid distortion from heat treatment, steel manufacturers offer it pre-hardened steels containing between 0.06 and 0.10% sulfur. And man, it machines beautifully. But here's the catch. That high sulfur content completely wrecks its polishability. So if you're designing a mold for clear, optical parts, like maybe a camera lens, that high sulfur steel is literally useless to you.
Furthermore, your steel block is bound by some very strict physical realities. The overall mold base size, the opening stroke, and the maximum ejector stroke are totally dictated by the real-world specs of the injection molding machine you're using. Take a look at these constraints for a Sumitomo SE50 EVA machine. If your mold requires more than 70 millimeters of ejector stroke just to push the part off the core, or if the whole thing physically doesn't fit between those 360 millimeter tie bars, well, your design is going to fail on the production floor no matter how awesome it looks on your computer screen.
Finally, we've made it to Section 6, bringing it together in CAD.
And here we see the grand finale. This is the unified, fully functional 3D design block. Everything we've discussed today is packed in here. The specialized steel plates, the precisely calculated runner and gating systems, the carefully designed cooling channels, and that scaled-up geometry accounting for anisotropic shrinkage. It is all combined into one cohesive digital assembly, fully prepped and ready for the CNC machines.
But let's be real, modern products are rarely just simple shapes. For complex parts that feature undercuts, think things like snap fits or side holes, a basic open and closed mold just won't cut it. The part would literally be trapped in the steel. Thankfully, modern CAD software allows engineers to seamlessly integrate advanced moving modules directly into this digital twin to solve those geometric traps.
Designing these integrated slide blocks is honestly a masterclass in kinematics. As the mold opens, angled pins actually force these slide blocks to move laterally, pulling the steel out of the undercuts just before the main ejector plate fires. This brilliant mechanism ensures that even the most ridiculously complex geometries can be reliably demolded every single cycle without damaging the part or the precision cavity. Wow, we've really covered an incredible amount of ground today. From that initial analysis of a plastic part, to the complex fluid dynamics of gating systems, right down to the metallurgy and advanced kinematics of ejection. It's a deeply complex, incredibly fascinating workflow. But I want to leave you with a bit of a provocative thought as you continue your engineering studies. As CAD software becomes increasingly intelligent, automatically generating optimal parting lines, calculating complex thermodynamic shrinkage, and simulating fluid flows with a click, will tomorrow's engineers still be designing these molds piece by piece? Or will your job shift to overseeing and optimizing the artificial intelligence that does the heavy lifting? Keep that in mind as you head into the lab. Thanks for learning with me today on this explainer.